So welcome to one of the last sessions of this year's chess. So this is the sensors session, as you know. We have free talks in this session, two in person, actually from the same person, if I'm not wrong, and one online presentation, a video presentation. And the first one is YTI, a tiny self-calibrating sensor for power variation measurement for in FPGAs. And our speaker is Brian Udugama.
Yeah, thank you. Yep, thank you. So this talk is going to be about VT, an area efficient on-chip sensor that can calibrate itself to measure power variations on an FPGA, and it can be used for remote power analysis attacks. So over the coming 20 minutes, I'm going to talk about on-chip power sensors, and I'm going to talk about remote power analysis attacks, and then we are going to look at the design of our proposed VT sensor, and then we are going to see some performance evaluations of our VT sensor. So first of all, on-chip power sensors and remote power analysis attacks. On-chip power sensors, they basically measure variation in signal propagation delay. And so propagation delay variations are related to changes in the operating condition, such as supply voltage. And what happens when the power consumption increases is that it causes the supply voltage to drop. And as a result, the propagation delay do vary. And what we can do is therefore we can use the signal propagation delay as a measure of the power consumption. So existing on-chip sensors, we have time to digital converters and ring oscillators. So these two were actually invented a while ago for a different purpose, but now they have been used for remote power analysis attacks. And we are going to look at VT sensor during this talk. And in the coming talk, I'm going to talk about another sensor. So remote power analysis attacks, they basically extract cryptographic secrets by analyzing the power consumption. And they use on-chip power sensors rather than physical measuring equipment such as oscilloscopes. So given that they are using on-chip sensors, we can perform remote power analysis attacks remotely without even not having physical access to the targeted chip. So as you can see here, in traditional power analysis attacks, we need a measuring equipment which would give us the power trace, but on remote power analysis attacks, we are using an on-chip sensor that gives us the power trace, and deploying this requires no physical access, so we can do remote power analysis attacks on a device that we have no physical access to. And the typical target for remote power analysis attacks is AES. And again, remote power analysis attacks are sort of a good indication on the sensitivity of the on-chip sensor, because we are looking at small power fluctuations. And to evaluate how good the remote power analysis attack is, we are going to use key rank as the performance metric. And key rank, it's basically the key of the correct key when all key guesses are sorted using the information that we recovered with the RPA attack. And key rank being it's a key, key rank being it's a rank, it gives us a decreasing value. So the lower the value is, the better the remote power analysis attack is. So we ideally want key rank to be 1, which means we have fully recovered the key. And some comparisons between existing sensors, time to digital converters, and ring oscillators. So if you look at the placement and routing, so ring oscillators, we can place them arbitrarily, but time to digital converters, we can't place them wherever we want because they got a long carry chain, and that constrains where we can put them. And if you look at some characteristic features, ring oscillators, they got a combinational loop. And the bad thing with combinational loop is that they are used for power viruses, and in cloud FPGAs, now they are being blocked, so you can't deploy ring oscillators on cloud FPGAs. And at the same time, with time to digital converters, we have latches, and latches, they are not very preferable in sequential circuits because they are it gives us a hard time in figuring out the propagation time. So, and in addition, they got long carry chains, which can be visually observed on the floor plan. And on the other hand, time to digital converters, we can perform a successful attack with just one sensor, but ring oscillators, we need several of them, usually about 64. And then the next thing, resource requirement per sensor. So time to digital converters, they are pretty good at, they require pretty high resources. They each, though one sensor works, that sensor needs about 34 FPGA slices, but ring oscillators, one sensor just needs 2 FPGA slices, but note that we need about 64 of them, which means we need 128 FPGA slices for a good remote power analysis attack. And then the alignment of the samples, time to digital converters, we get aligned samples, but ring oscillators, they can be misaligned. And all in all, we can see that there are some preferable features that we would like to have on an on-chip sensors, like arbitrarily place it and route it, and then to have an attack done with one sensor and having lower resource consumption, and then producing samples that are aligned. So those are some preferable things that we would like to have. But given that the existing ones were defined for some, were designed for some other tasks, they are not giving all the desired features, but they do have some desired features. But so with these ones having in mind, let's have a look at our proposed VT sensor design. So it's the block diagram of VT looks like this, and the key components are as shown here. So the first one we are going to look at is this I delay G element, which is identical to the following I delay C element as well. And so it's basically an adjustable input delay element. We can visualize it in sort of like a volume slider, which we can slide it. But instead of the volume, we can change the delay that it induces on the signal that it passes through it. And so the next part is this step delay line, which is essentially a series of cascaded AND gates. And we know the AND gates produces 1 as the output when only both the inputs are 1. So we are going to use that property here. So when we want to enable the sensor, we set this enable signal to 1. Then immediately these points will become 1 as well. And then when the clock rises, what happens is, so we have this point becoming 1. And then the signal propagates through this I delay G element here. And of course, it takes a bit of time and that time is determined by the designer. And then what happens is this TDL in becomes 1. So now the first AND gate got both the inputs 1. And after the signal propagates through the AND gate, we would see a 1 at its output. And this now we can see that the second AND gates got both the inputs being 1. So the signal would propagate through it, taking a bit of time, and we would see an 1 at its output. So the same thing goes on. And while that's happening, we have another path where the signal can propagate. So what happens there is when the clock is 1, we have the signal propagating through the ideal AC element, and it triggers the clock signal for these flip-flops. Now, both of these things happen at the same time. So let's have a look at how things would happen when both of these things work simultaneously. So while the signal propagates through the TDL, and then halfway through the clock would trigger. So what would happen is we would see a series of 1s because the signal managed to propagate through them. But for some cases, we would see 0s because the signal didn't reach so far. And so the clock triggered before actually the signal reached there. So then, as I just mentioned a while ago, the power consumption, it's proportional to the propagation delay. So when the power consumption is low, what would happen is the propagation delay is low, which means the signal can propagate quickly. So it would manage to reach a certain AND gate. So we would, by the time the flip-flops get triggered, so we would see some number of 1s followed by some number of 0s. But when the power consumption is high, what would happen is the signal would not manage to reach so far. So just before it reaches there, what would happen is the clock would get triggered. So instead of having many 0s, we would have fewer number of 1s. And so that's the key part of the VT sensor. So we have few more additional components to assist the key parts to work. This calibration FSM highlighted here, it's essentially the control logic that controls how much delay this IDelay G element induces. And then we got a memory to store the outputs from the flip-flops. And that's where the power traces are stored in. And so that's basically how the VT sensor looks. So the 4 features that we discussed and saw in the existing sensors, so VT satisfies all 4 of them. In addition, we managed to design a sensor that is in the resource requirement is independent of the clock frequency. So VT, no matter how the frequency is, we still need the same number of resources. And then we have this built-in automatic runtime calibration mechanism built into the sensor design. So a few performance evaluations with our VT sensor. So we specifically look at a 4-bit scenario. And so first we'll have a look at what happens when we move the AES module. So we picked 6 different placements for the AES module as shown here. And then we fixed the placement of the VT sensor and then their frequencies. So this is how the performance varies with the placement variation. So as you can see, regardless where we put the AES module, we can attack it. But of course, there's a noticeable difference between different configurations, but no matter where we put the AES module, we were able to attack it. Then we check the impact of the placement of the VT sensor itself. So for that, we varied the placement of the VT sensor to 17 different placements shown here, and then we placed the AES module down here. And again, we fixed the frequencies as well, and we collected power traces and we ran some power analysis attacks. So the performance variation is as shown here. So the figure to the left, it's the floor plan. And so we have selected few placements to represent the others. So one corresponds to one here, corresponds to one here. So 3, 9, 7, 16, and 17. So out of those 17 placements, we pick 5 of them to represent all of them. So as you can see, some of the cases we managed to get the key pretty quickly, but some cases they were not as good as the others. And so the color gradient we used here is, so we used green to say that it's easy to attack and red to say it's harder to attack. So we can see that there's sort of a clustering here. And so the takeaway point is, so the placement of VT has a significant impact on the attack efficacy. So then we looked at what effects do the temperature change has on its performance. So the thing is, on chip sensors, they are susceptible to temperature changes because a slight change in temperature would cause the operating condition to change, and therefore it would they are susceptible to temperature changes. So what we did was we slightly modified the calibration mechanism so that it would recalibrate when there is no change observed. And so we fixed the placements and the frequencies. And then what we did was while the AES module is executing, we blew hot air over the chip so that the chip gets warmer. And so this is how the variation looks like. So the graph to the left shows how we change the temperature, and the graph to the right is the corresponding variation in the key rank. And so with recalibration enabled, VT is capable of adapting to temperature changes, and specifically VT can respond to abrupt changes. So if you look at the yellow waveform, yellow plot here, so we blew hot air around 50,000 traces and we let it naturally cool down, and then around 70,000 traces we blew hot air again. So it was an abrupt change, but still we can see that it eventually converges, and we can see that we can fully recover the key at the end. And we also have a comparison between the resource efficiency of VT with then existing sensors. So VT, we just need one sensor, and the total resource requirement is just 8 FPGA slices and 2 of these IO delay elements when compared to 34 and 128 FPGA slices for the existing ones. And then we just need 1 block RAM to store the samples because it's each sample is fewer in bits. And the size of a power trace is almost half when compared to the time to digital converters. So in addition, we experimentally evaluated few more effects. So we checked how the frequency of the AS module affects on the efficacy. We checked what effects do the frequency of VT has. And then we checked the magnitude of the power variation on the attack efficacy. And also we checked few properties of VT. We checked whether it's portable, and also we checked whether we can deploy it in cloud. So we used Amazon AWS service to see whether we can deploy it in cloud, and then we actually managed to deploy on one of these Amazon AWS instances. Also, we checked whether it's noise tolerant, and we have shown the results in our paper. So for more results and information, kindly refer to our paper here. You can scan the QR code and it would direct you to our paper. And we have the design sources and sample data sets submitted and accepted as artifacts. And you can refer this link for the artifacts associated. And so in conclusion, in this talk, we looked at on-chip power sensors and their characteristics. We looked at remote power analysis attacks and what key rank is. We looked at the design of our VT sensor, and we looked at performance and properties of VT. So it's time for questions.
Thank you very much for the talk. I'm just checking if we have, could you help with me? Any questions? Yeah.
Hello. Thanks for the presentation. I'm wondering how much did you experiment with the oversampling ratio? Because you have this fixed parameter of 16 times oversampling used now.
I didn't get it though. Can you repeat? Sorry.
Yeah. How much did you experiment with the oversampling ratio? Yeah, this 96 megahertz.
Yeah. Okay.
Yeah.
So we had so the AES module was executed at 6 megahertz, and then we did sort of oversampling just to make sure that the samples actually didn't matter very much though. But we just did we ran the circuit at a higher frequency, just sort of having a redundancy, but it didn't matter anyways. Yeah. So there are other results. In fact, oh, why didn't it work? There are some other results actually, like on the paper, we have shown some results which we were managed to break AES with the same frequency as the sampling frequency.
All right. Thank you.
Did I answer your question? Or?
Yeah, it sounds like I need to read the paper.
Okay.
Any other questions from the audience?
Yeah.
Oh yeah. Sorry.
So, can you tell me a little bit more about why you are saying that it is auto calibrating, and where do you store the calibration data, and how do you utilize the calibration data actually?
Okay, so
there is one more question. Maybe you can answer this and I can ask the next one.
Okay, so basically calibration, what we do is so it's more like, to visualize, it's more like I'm adjusting that a volume slider kind of a thing. So with a logic circuit, I let it calibrate to a point where I could start seeing the variation happening. And then we just lock it there afterwards.
So you mean to calibrate the IO delay module, but not the output of the flops, which you are storing in the memory?
No, so we look at the output of the flops, of course, but that's being fed as an input to the IO delay, the logic circuit. But then we just calibrate the IO delay element itself.
Okay. And the last question from my side is, I mean, what's your how do you recommend this? I mean, what's your conclusion out of this entire activity? Do you feel that one should not put sensors near the AES operations, or how do you recommend basically to utilize this?
Okay, so I think there are a couple of takeaway points from this work, I guess. So the first one, I think it's more about the vulnerability of itself. So it's hard to assume that not having physical access means that it's safe, given that there could be some other sensor on chip itself which could measure it. And then so in the sense of a victim, there are more things to consider other than physically isolating the targeted chip. And then the other takeaway point probably is using these kind of sensors. So of course, blocking sensors makes it's not a very I don't think it's the approach, because maybe these sensors might have other use cases as well. So so it's sort of a, I think our intention was to show that there is this vulnerability, and then yeah, that's what we were
And
intending.
one last question, sorry,
Yeah.
is this sensor 17 was in red color. That means it was not able to detect the key with the help of that sensor number 17 in the diagram that
Yes,
you
yeah.
showed,
So
which was very near to the actual
yes,
victim
yeah.
design, and the farthest one
Further
could do
ones
that.
work. So
Any correlation between the two?
in fact, it's more about the routing delay. So how the routing delay itself affects the sensor's performance. So it's more like because all these components, they have discrete delay values, right? So we can't have sort of smooth transition. So we can't have sort of a smooth curve. It's all sort of like jagged sort of changes. So what happens is, if the delay doesn't align properly, then it would not work as we expect. So it's because all of these are like quantized values, not like smooth values.
Okay, thank you very much. So we have the second talk, like video. While setting that up, there is an announcement.
There's a small practical announcement. So the organization found the passport of Namhoon Koo. So I repeat, that's Namhoon Koo. If you are this person, your passport is at the registration desk in PDS. Okay, that's the other auditorium. And if you know this person, please tell them to come pick up their passport. Thanks.
And and I just want to thank all of you for your attention and for thoughtful questions. And the slide had some other, so I would like to thank chess organizers and sponsors for sponsoring
Yeah,
sponsoring me with
thank
this
you.
event. Thank you.
Thank you very much. Let's thank the speaker again. Yeah. Okay, so are we ready with the video? Okay, so I'll just need the presenter's name. Here. I cannot see it on the Zoom yet, probably.
Yep, I'm here. Hello.
No, okay.
Hello. Can you hear me?
Let's do it from here. So our second talk will be, as I say, like recorded. It's PreemSat, preventing magnetic saturation attack on Hall sensors. It will be by Anomadarshi Barua. So I think we can start the talk and we can take the questions later.
Hi everyone. I am Anamodar Shiburwa from UC Irvine. I am going to present one of our works today. Our work is related to a defense methodology for next generation Hall sensors. We name our work as PreemSat, which has a full form, preventing magnetic saturation attack on Hall sensors. Before going to present our main work, I want to give an outline of this presentation first. We will start our presentation giving a generalized view of Hall sensors, indicating their operational basics, market growth, and vulnerability in detail. Next, we will define the saturation attack and motivate you about the importance of our work by indicating the lack of work along this direction. After that, we will start explaining our defense PreemSat. We will also present a prototype of our defense with proper justification and evaluation. And at the end, we will conclude our presentation indicating the limitations of our defense. Now we are going to start by giving the market growth of Hall sensors. At the very beginning, let's give some foundational knowledge on economic growth of Hall sensors in today's market. Hall sensors are so abundant, prevalent in today's sector-critical systems. Hall sensors are everywhere. It has been estimated that Hall sensors market size is expected to grow from USD 80 $831 million in 2016 to USD 1,473 million by 2023. We can find Hall sensors in industrial controllers, in power systems, in automotive industry, and also space aircrafts. Therefore, Hall sensors are pervasive and works in ears and eyes of many safety-critical systems. And therefore, the security of Hall sensors is really important. In this slide, we will discuss different components of Hall sensor basics in general. We'll start from the Hall sensor physics. As we can see from this figure, the main component of the Hall sensor is the Hall element. This Hall element is typically a p-type semiconductor. A DC voltage bias is applied across the Hall element that causes a bias current flowing through the Hall element. A magnetic field is also applied on the Hall element in a perpendicular direction of this bias current. Because of this perpendicular presence of the bias current and magnetic field, a voltage will be generated across the Hall element. This voltage is known as Hall voltage. The generated Hall voltage is proportional to the magnetic field. Next, we will discuss what other electronics Hall sensors have in addition to a Hall element. The output of the Hall element is given to a signal conditioning block, which has a differential amplifier. The differential amplifier amplifies the Hall voltage and also removes the common mode noise from the Hall voltage. A regulator is also used to provide supply voltage and stable bias current to the Hall sensor. Next, we discuss the linear and saturation region of the Hall sensor using its transfer curve. The output of the differential amplifier is linear within a certain region. This is known as the linear region of the sensor. Sensors operate in this linear region. The sensor output voltage begins to flat when the supply voltage limits are reached. This flattened region is known as the saturation region. In this saturation region, no information can be recovered. In this slide, we will discuss the vulnerability of Hall sensor hardware and also define the attack model. As we can see from this figure, the main component of a Hall sensor is the Hall element. The output from the Hall element passes through differential amplifiers, filters, ADCs, and eventually arrives in the main connected system. It is clear from the discussion that there is no hardware-software parallel present between the sensor and the system interface. Therefore, this could be an entry point of an attacker. A smart attacker can non-invasively inject fake external signals into sensors by using a simple low-cost electromagnet. The injected fake signals can eventually spoof the Hall sensor in its linear region or drive the sensor to its saturation region. We name this attack as the saturation attack. In this saturation region, no information can be recovered and the sensor faces a denial of service attacks. We already defined the saturation attack in the last slide. Now we are going to motivate you about the importance of our work by indicating the lack of work along this direction. There have been quite a few works on sensor defense over the last 6 years. This table indicates the list of those work. If you observe this table, you can see that no work exists to prevent a saturation attack on Hall sensors. People are using different shielding and filtering techniques to prevent the spoofing in the linear region, but none of them actually prevent the sensor from going into the saturation. The reason behind this, these filtering techniques occur as post-processing after the sensor sends the data. Therefore, if sensor is already in the saturation, no amount of post-processing after the fact can actually help. So we need a defense that can work before the post-processing of the sensor data. Now we are going to discuss how our defense work against the saturation attack before the post-processing of the sensor data. The main strategy is we will not allow the Hall sensor to go into its saturation region. The next question comes, how will we ensure that the Hall sensor will not go into its saturation region? We will ensure this by providing the same amount of internal magnetic field in opposite polarity to nullify the injected fake external magnetic field. This is explained with an animation here. As you see in this animation, if we can provide the same amount of internal magnetic field to the sensor in right direction or in appropriate direction, it can nullify the external fake magnetic field. This will prevent the sensor from going into the saturation region. Now we explain in which direction we need to generate that internal magnetic field to nullify the external fake magnetic field. We need to remember that not all components of the external fake magnetic field can influence the Hall sensor. Only the vector summation of all the vertical components of the external fake fields can only influence the Hall sensor. This is called by BV external. Let's explain this with this figure. According to Lorentz force, the Hall voltage is only sensitive to magnetic field B, which is perpendicular to bias current I bias. Therefore, if there is one or more multiple magnetic sources are present for the attack, the Hall element is only sensitive to the vector summation of all the vertical components of the external fake fields, which is shown here with the blinking arrow. Now we know from the previous slide the vertical component can influence the Hall sensor. To collect this vertical component from the external magnetic fields, we use a low resistance circular toroidal magnetic path made with ferrite core, and we place the target Hall sensor within the gap of the toroid. We use a primary coil wrapped on the same toroid to generate the internal magnetic field to nullify the vertical component of the fake external field. This concept is explained here with this animation. If you notice here, the blue one is the fake external field inside of the toroid, and the gray one is the internally generated magnetic field by the primary coil, which has same strength and in opposite direction of the blue one. Therefore, the gray one is nullifying the blue one inside of the toroid. In this way, the external fake field can be nullified to the internal field using our defense frame set. The right figure is the physical implementation of the toroid with the primary coil. Now we explain the different blocks of our defense in detail. The circular toroidal core is already present or explained in the last slide. The toroid also hosts a secondary sensor to sense the magnetic field present inside of the toroid. The output from the secondary sensor is amplified and noise cancelled using a differential amplifier. Next, the signal from the differential amplifier is digitized using an analog to digital converter and feed into a CPU. The CPU actually runs an algorithm which generates a digital signal to nullify the magnetic field present inside of the toroid. This digital signal from the CPU is converted into an analog signal using a digital to analog converter and feed into the primary coil using a power buffer. Next, the primary coil generates the internal field inside of the toroid to nullify the fake external field. The nullification process already is explained in the last slide in detail. Now we discuss the algorithm which runs on the CPU. The algorithm is a PID controller. The PID controller takes the fake external field as the reference signal. The Kp, Ki, and Kd constants of the PID controller are chosen in a way to have the same response time. The PID controller is implemented in the Z domain instead of the S domain or continuous time domain to make the PID controller more stable and deterministic with fast response. The output from the PID controller is converted into an analog signal using a digital to analog converter that is fed into the primary coil. Next, the generated internal field is again provided as a feedback to minimize the error between the external and internal field. This iteration continues until the internal field is equal to the external fake field with a minimum error. In this way, the PID controller ensures that the generated internal field has the same strength as the external fake field to nullify the external fake field completely. In this slide, we discuss the prototype and the test bed to evaluate our defense frame set. We use a strong electromagnet as the source of the external fake field. A manganese zinc soft ferrite is used as the turret core in our prototype. We also use a low power op amp as for the differential amplifier. An EFM32 Giant Gecko development board from Silicon Labs is also used as a CPU to run the PID control algorithm for our defense. We use an Arduino board to control the external fake magnetic field generated by the strong electromagnet in our testbed. And an antenna is also used to inject EMI interference into the prototype in our testbed. In this slide, we will justify the effectiveness of a defense frame set against the saturation attack. The first figure is the output from the Hall sensor before any attack happens. And the second figure is the output after an attack happens. You can see that the output of the target Hall sensor is driven to its saturation voltage close to 4.8 volt after the saturation attack, which results a flattened output signal. Next, we integrate our defense frame set with the Hall sensor. The output signal after the attack when we use frame set is shown in this third figure. Next, we measure the similarity between the output signal before the attack and after the attack when our defense is present using the correlation coefficient. We find that the correlation coefficient between these two signals is close to 1. This indicates that the output signal is not perturbed even after the attack when we use our defense. This gives justification of our proposed defense against the saturation attack. This slide presents the result after evaluating the defense frame set with 10 different Hall sensors from 4 different manufacturers. We tested frame set within the entire frequency range of 10 different Hall sensors. You can see the similarity or the correlation coefficient is close to 1 when we use our defense. This proves that our defense frame set works within the entire frequency range of the Hall sensors. Next, we test our defense frame set against different strength of the external fake magnetic fields. You can see our defense works up to 4200 ampere turns, which is really a strong field and maintain a correlation coefficient close to 1. As we tested our defense for 10 different Hall sensors, we can say that our defense is quite general to the Hall sensor. Now we are going to compare our defense with a ferromagnetic shield. This will answer the question whether our defense is better than shielding. We know that the increase of the shield thickness provides better shielding. Therefore, we vary the shield thickness from 0.3 inch to 1 inch and measure the correlation coefficient for every sensor. We can see that even 1 inch shield cannot prevent a strong magnetic field. It is evident from the value of the correlation coefficient, which are less than 0.5. Because shields get saturated at high magnetic field, therefore its shielding property gets diminished. Next, when we use frame set only, we can see that the correlation coefficient is close to 1. This indicates that frame set is more effective than a shield. Now we discuss on the limitations of a defense frame set. These limitations exist because of the practical limitation of the hardware, not for the design methodology. Frame set consumes 0 to 3 watt power while generating the strong magnetic field. This power consumption may be small for some applications such as solar inverters, but may be substantial for few applications such as proximity sensing. Non-zero settling time of 23 microseconds of the PID controller contributes to the real-time requirement of the defense. Therefore, if the attacker changes the injected fake magnetic fields within 23 microseconds, the timeliness of the defense may not be guaranteed. In spite of the fine-tuning, the PID controller has a non-zero steady-state error, which may add small error to the internal field while nullifying the external field. Our prototype can prevent an external magnetic field up to an MMF of 4200 ampere turns. This limit can be theoretically increased to any value using a stronger buffer. Our prototype can also prevent the external magnetic field up to a frequency of 30 kilohertz. This upper limit results from the total time required to generate the internal magnetic field. This time can be reduced further using a faster CPU having a clock frequency higher than 48 MHz. We are close to the end of our presentation. Now we provide a summary of our work. We introduce the saturation attack model and lake of work along this direction. We provide a defense against the saturation attack for Hall sensors. We also provide a prototype, justification, and evaluation of our defense. And last, we also provide limitations of our defense. Yep, that's all for today. Thank you very much for your patience and time to listen our work. I'm happy to answer any question if you have.
We thank the speaker for the presentation.
Thank you.
We have Anamodarshi on Zoom side, so in case you have any questions, please feel free to ask. Can you hear us, Anamodarshi?
Yeah, I can hear you. Can you hear me?
Okay, that's great. So far, I haven't seen any questions on the Zoom side. I'll just double check. Any questions from the audience? I cannot see any. I may have one question regarding the limitations you mentioned. So about the power in the last, I think it was the slide before the last one.
Yep.
Do you investigate anything, or have you investigated anything to deal with that, or you just accept it as it is?
So the numbers, the 0 to 3 watt power consumption, like actually the 3 watt, that is the extreme scenario. So for example, the power consumption solely depends upon the how much magnetic field the attacker is exerting into the sensor. So the 3 watt power is the extreme condition. So normally the attacker actually can generate that amount of power in a practical scenario. So normally the amount of power the attacker can generate by using the EMI or electromagnet is closely range less than 1 watt. That type of power is actually feasible for solar inverters or the autonomous or the industrial controllers. Like the power is not an issue actually. But for few applications like the proximity sensing, where the low power is actually used, maybe the 1 watt could be critical. So one way to actually reduce this power is actually omit that power buffer thing, because that is the most power hungry device that actually consuming the high power. So if we remove the power buffer, we can actually somehow reduce the power consumption for the current scenario. But if we reduce the power buffer, like the one problem could occur is that like the primary coil actually cannot generate enough power to counteract the exerting magnetic field. So it's actually a trade-off, like how much power we actually spend or how much magnetic field we actually nullify. So it's some kind of trade-off actually.
Okay, thank you very much.
Yeah.
I think we don't have any questions, and we anyways have to switch to the next talk. Thank you very much for
Thank
your
you.
presentation.
Yep.
Let's thank the speaker again. So I will just get him to talk again. Great. So we again have Brian for the last talk of the session, a power to pulse width modulation sensor for remote power analysis attacks. So
Thank you. Yeah, so in this talk, we are going to look at power to pulse width modulation sensor, or PPWM. It's a self-calibrating on-chip sensor that's designed for remote power analysis attacks on FPGAs. So in the previous talk, we looked at what on-chip power sensors are, and we looked at what remote power analysis attacks are. And in this talk, we are going to look at few design insights to design for designing better RPA sensors. And then we are going to look at the architecture of the proposed PPWM sensor, and then we are going to see some performance evaluations of the PPWM sensor. So the design insights, first of all, we are going to look at the sensor resolution. So we are motivated. So for this, we were motivated by the sensor output of VT. In fact, VT had a lower resolution compared to then existing sensors, but its performance was no worse than them. So what we did because of that, what we did was we synthesized a set of power tracers with 8-level resolution, and we added wide Gaussian noise to simulate a real world scenario or a real world on-chip sensor. And the outputs, we had them in the range of 0 to 7. And we used data binning to bin them into different number of, so just to reduce the resolution, we did data binning. So we had the original traces as it is with 8 bins, and then we combine few bins together to get 6 bins, and then we pairwise bin them, so we have 4 bins, and then we split them into 2 halves, so we got 2 bins. And then using those traces, we performed remote power analysis attacks, and this is how the result looked like. So here, what the plot, what it shows is, so we have overlaid where the attacks were successful with 8 bins. On top of that, we have overlaid the places where we were able to attack with 6 bins, 4 bins, and 2 bins. So, and then our y-axis, top to bottom, we have increased the noise in log scale, and x-axis, again, we have increased the noise in log scale. Sorry, we have power traces increasing in the log scale. So you can see at a glance that the place, almost all the circles with where the lighter color circle is, you can see the darker dot. So which sort of means that the number of bins doesn't matter, because with 8 bins, almost all the places where you could attack with 8 bins, you could attack with 2 bins as well. So in a way, what that means is like the attack efficacy is not compromised by lowering the resolution. So we could make a 2-level sensor, which means like there's only 2 bins. We could make such a sensor, and that should be sufficient for remote power analysis attacks. And why such a motivation? Because with 2-level sensor, we could possibly lower the resource requirement of the sensor because it's smaller. And given that it's just 2 levels, it just the information is just 1 bit, and therefore the bandwidth requirement is lesser. If you want to transfer the trace from the sensor to an attack setup, the bandwidth requirement would be lesser. And given that we could make it smaller, we could make it stealthier when compared to bulky sensors. So next, we are going to look at the impact of the threshold value. So what I mean by threshold value is where we should split these 8 levels into 2 bins, which place we should do that binning. So for that, we investigated the ideal threshold value. So we tried splitting it between 0 and 1. So 0 goes to 1 bin and the rest goes to another bin. So we tried changing the bins to different values. So we tried all the way up to 7. So we had 8 different bin configurations. And so we used those bin traces to perform RPA attacks. And this is how the results looks like for that. So again, in this plot, what I have shown here is we have so this purple dot, it's showing the thresholding happening at 0, and then on top of that we have overlaid different places that we threshold. And again, like in the previous plot, we have y-axis noise increasing in log scale from top to bottom, and x-axis number of power traces increasing in log scale from left to right. And so again, here you can see at a glance that the darker dots are not as widespread as the lighter ones. So you can see more, the lighter ones are widespread, more widespread compared to the darker ones. So if you look at specifically this A square, it's at a glance you can see it's darker when compared to the other, which is because you can see these edge cases in that square. But if you look at B, we don't have these, the darker, the outermost ones. So in the sense, we were only able to attack with, if we were splitting it in the middle. And then C, it's the lightest, which means none of these darker ones exist. So we were able to attack only with the innermost thresholding values. So essentially, we would have thresholding between 2 and 3, 3 and 4, 4 and 5 here. And so that's where we would like to have the thresholding happening with the sensor. So the takeaway point is, so the attack efficacy is significantly reliant on the thresholding value, and incorrect threshold value in this, so it actually causes a significant performance degradation. And when compared to the sensor resolution we just discussed a while ago, threshold value actually matters. So it's actually important to make sure that we threshold it at the correct point. And so with those things in mind, let's have a look at the architecture of Ppwm. So this is how the sensor design of Ppwm looks like. And the key components are the ones that are shown here. So we are using XOR gates in this design. So XOR gates, the key property that we are going to utilize here is that XOR gates would give us a 1 when the inputs are different. So for the moment, let's assume the sensor is stable and the clock is 0. So all the points, all the junctions in the sensor they are settled to the 0, to the logic 0. And for the moment, we'll just worry about this part because the rest it's pretty similar to the part that we are going to discuss. So when the clock rises, what happens is this would become a 1, and immediately these 2 points will become 1s because it's just a straight wire. Then now, unlike in the previous case where this was 0, the XOR gate sees 2 different values in its inputs. So what that does is that the XOR gate would output a 1 because the inputs are different now. And after the signal propagates through this buffer, this input of the XOR gate would become a 1. So now again, the XOR gate would have the same inputs, which would cause this to become a 0. So if you look at it again, what happens is when the clock rises from 0 to 1, we would have a pulse generating at the XOR gate output. So we know that, as I discussed in the previous presentation as well, so the power consumption is proportional to the signal propagation delay. So what happens when the power consumption is low is that it would cause less delay on propagating the signal along the buffer. So it would quickly propagate. Therefore, we would have a narrow pulse occurring at the end of this XOR gate. But when the power consumption is high, it would cause higher propagation delay. So it takes time to the signal to propagate. So the result would be that the XOR gate would generate a wider pulse because the signals were different for a longer period of time. So now the blue gate network is the one that we discussed. So we see that the red one, it's identical to the blue gate network, but in addition, we got an IDLA element connected to that. So IDLA element, it's the same thing that I discussed in the previous presentation. It's more like a volume slider, but in this case, what happens is when we slide the delay, we could offset where this pulse is appearing. So we could use that to sort of slide where the pulse is appearing, and then we have an AND gate, which is driven by these 2 waveforms. So AND gate, it would output a 1 when both the inputs are 1. So when the signals are aligned, we would see that we should be getting almost identical pulse. But if we use this ideal element and shift the value, what happens is we can control the width of that pulse appearing at the end of this AND gate. And then what we do is we use this AND gate output to drive the clear input of a flip-flop. And the flip-flop is constantly fed with 1. So we use that to drive the clear input. So, and all the signals, they need to be held for a certain period of time for the effect to get for its effect to get actually affected. So if we have the IDLA value at a certain if we use it at certain point, regardless the power consumption, we can see that this waveform satisfies the minimum time that the clear input requires. So regardless what the power consumption is, it would always clear the flip-flop. But if we move it a little bit, you can see that the pulse width gets narrowed, but still regardless the power consumption, you can see like it when the power consumption changes, the width changes, but still it satisfies the minimum time required for the clear input. So no matter what it is, it would still clear the flip-flop. But if you move it a bit further, you can see that in some cases it satisfies the minimum time required for the clear input, but in some cases it's narrower than the minimum time required. So it's not satisfying that requirement, so it's not going to clear the flip-flop. So when the power consumption is low, we saw that the pulse width is narrower. So for a given I delay setting, let's assume that it gives us this sort of waveform. So it's not going to satisfy the minimum time required for the clear input to get affected. So as a result, we should be seeing a 1 at the flip-flop output because the clear signal is not affecting, and we should see the data reflecting at the Q output. But if the power consumption is high, for the same I delay setting, we would have a wider pulse. And what happens is, so it should, no matter what the data value is, it should clear the flip-flop. So we should see a 0 at its output. So that's the core part of PPWM. And then we have few more components to assist its functioning. So this control FSM, it's basically the one that determines whether we should adjust the I delay or not. And then we have a memory to store this flip-flop output. And few performance evaluations of PPWM. So we checked the impact of the AES module, the frequency of the AES module. So we placed the PPWM sensor there and the AES module here, and then we varied the frequency of the AES module. And so the results looks like this. So you can see that the key rank variation, it's sort of encapsulated within a narrow envelope. Oops. So specifically, you can see that the sampling frequency to the AES frequency seems to be not that relevant because we have varied the frequency in a quite a wide range, but the performance still looks the same sort of. And then specifically this red waveform, the red variation, the AES was running at 96 megahertz and the sampling was done at 96 megahertz, in the sense both were running at the same frequency and still we were able to attack the AES module. And we checked the cloud deployability and portability of PPWM. For that, we used Amazon EC2 AWS instance. So to check portability, we actually deployed the experiment setup concurrently in 2 different instances. And so these F1 instances, they got new Xilinx Ultra Scale Plus FPGAs, and we used these frequency settings. So we used the sensor at 200 megahertz and the victim AES at 10 megahertz. And this is how the key rank varies. And so as you can see that in both the experiment setups, the efficacy was pretty similar. And the conclusion is that an attacker could use a different instance to design and test a sensor and then deploy it along with a victim and expect near identical performance on that setup as well. Also, we did some comparison with existing sensors. So we compared ring oscillators, TDCs, VT, and PPWM. And for ring oscillators, we use 64 instances, but for other sensors, we just use one of them. And we used same frequencies for all the test setups. And this is how the performance varied. So we can see that for the given configuration, PPWM outperformed all the other sensors, but we can consider them to be of comparable efficacy because with a small change in the routing delay, this could actually change how long it takes to recover the key. So it, in a way, we can consider them to be of comparable efficacy, but with our recalibration mechanism, we have made sure sort of the key of the thresholding point or the routing delay impact would be minimal. So in addition to those results presented, we experimentally evaluated the effects of the placement of both the AES module and the PPWM sensor. And then we checked the impact of the temperature change. And we experimentally evaluated few properties, specifically the bandwidth requirement of the sensor. And for more results and information, kindly refer to our paper. And we have submitted design sources and sample data sets as artifacts, and they have been accepted. So I think they should be available with ISER soon. And if anybody needs them upfront, please do email us. We can send them if you want to do before they become available through ISER. So in this talk, we looked at the impact of the sensor resolution on RP attacks, the impact of threshold value on RP attacks, and then we looked at the architecture of the proposed Ppwm sensor and its performance and properties. And it's time for your questions.
Thank you very much for the talk. Any questions from the audience? I haven't seen anything so far on Zoom. Let me double check. There is one meanwhile from the audience.
The new sensor that you introduced,
Yeah.
what was its characteristics to the temperature changes, if you have done that?
Oh, yeah. So we have them in the in our paper. So given that it's almost the results, so we picked few for the Ppwm and we picked a remaining set for VT. So just so that they're sort of so you can get some idea, because we didn't choose the same to show because it would look like the same. So you can actually go through the paper and we have the results there.
Which one is more resilient between the two architectures?
I would say it's of course the performance, of course, for the tested conditions, they were pretty similar. I think we should properly do an experiment and conclude something like that. It's a bit hard to conclude
Do
with
you
that.
think the new architecture, this one, Ppwm, would be less resilient to temperature than the previous one, because you might increase the resolution of your measurement by adding so many AND gate structures as compared to in this where your
There's only one point that
the one IO delay only basically.
I suspect that though, but the thing is, by recalibrating, what I do is basically I change the IO delay setting. So it's the same IO delay setting change happening on both the sensors. The only thing which I could think why BT would work better is there are three more places where we could have the change trapped. No problem.
Any other questions? Anyways, we're quite out of time. Actually, is there any? Or do you see?
Yes. So to get to the PDS as quickly as possible, we will go
Yes.
via
Yeah.
these doors to make things
Okay.
go fast.
So now we conclude our session here, and also the last sessions of chess. Thank you very much for attending. Let's thank the speaker again. And as they said, you can use these doors to reach PDS again. Thank you.